Everybody, I want to spend a little bit time talking about problem 8 on homework set 7, where we're rolling a skee ball up and having a jump over a gap and land in some target here at distance d. So first off, the way the problem is set up, don't worry about the radius of the ball. We'll assume that it isn't specified or is specified, but irrelevant to the problem. The way to do this problem is to kind of work it backwards. You know that you need to leave the top point on the ramp here and go ahead and say, okay, from there we're going to execute a projectile motion problem and land here inside the target. For that, we know that there's a range formula that says that the distance that the skee ball travels is going to be equal to v top squared over g times the sine of 2 theta. And we're lucky because this theta here, the launch angle, is actually the theta specified in the problem. So we can go ahead and use whatever you have for your theta there in place of the launch angle. And then we have our v top here being the launch here. What we need to do is find out the initial speed down here at the bottom, given that we want to launch from v top. And that turns out to be an energy problem. So we can say that the energy at the top minus the energy at the bottom is going to be 0, since there aren't going to be any non-conservative forces in our problem. So we have no non-conservative works. At the top, I have the kinetic energy of the ball plus, I'll call it K top, plus the potential energy due to gravity. And at the bottom, I have the kinetic energy of the ball at the bottom minus the potential energy at the bottom. And that's 0. Now for this case, we're going to have UG top and UG bottom. So UG at the top is just the mass of the ball times the gravitational constant times the height at the top, h top. UG bottom is just going to be mghb. And then what we can do is you can say, well, if I take the potential at the top minus the bottom, this term is just going to be UGT minus UGB is mg times the height difference, ht minus hb. And then from that, I can use trig in this problem to say, well, look, I've got SOHCAHTOA, and so then my ht minus hb is just going to be mg times L sine theta. Now, I apologize for going through this in great and gory detail, but I think it's good, since we had some issues with the work energy theorem on the midterm exam, just to tabulate where everything was coming from. So then we have to have the kinetic energy at the top and the kinetic energy in the bottom. And to figure out the kinetic energy of these two situations, we have to know that the ball is rolling without slipping. So the kinetic energies, K, in general, are going to split into two parts. So you're going to have 1/2 at mass of the ball times the velocity, or the speed at which it is traveling. And then you're also going to have 1/2 I omega squared, where omega represents the angular speed with which it is rotating. So this is going to split into two parts. And that moment of inertia controls how much of the energy has to go into rolling versus how much has to go into moving the center of mass. And if we're rolling without slipping, we further have the relationship that the speed with which it is rolling is equal to the radius of the ball, r, times omega. And as we've done in lecture, you can go ahead and make this substitution in here to find out that this means that the kinetic energy is equal to 1/2 mv squared times 1 plus moment of inertia divided by mr squared. And if I have that moment of inertia divided by mr squared, this first term is telling me about how much of the energy goes into moving the ball, and the second term tells me how much energy goes into rotating the ball. Now we also know that for a sphere, that I is equal to 2/5 mr squared. So this term is 1 plus 2/5. And so the kinetic energy in any of these situations, either top or bottom, is 1/2 mv squared times 1 plus 2/5, known to the world over as 7/5 or 1.4. So I can say that this is 7/10 mv squared. See what I did there? It was totally a bit of adding fractions. Now we've got all of these kinetic energies, and these apply to the top as well as the bottom. We're after what the bottom speed is, so I can go ahead and use the 7/10 mv squared here in the bottom term and solve this entire equation for b bottom in order for the top and to give me this relationship here. So this is the key, is you have to work it backwards. You know it has to land here. Therefore, at the top, it has to have this speed vt, and therefore at the bottom, it has to have the speed down here that you solve. So I hope that gives you enough tools to get going on this and walks through the whole notion of rotational kinetic energy in the case of rolling without slipping a little bit more. Good luck on the problem and the rest of your homework.